I'd like to talk a little bit about Avogadro's law and Dalton's law. Avogadro's law simply says, it's pretty straightforward, that equal volumes of gases at the same temperature and pressure will contain equal numbers of particles. So what ends up happening is you get a graph that looks pretty much like a straight line where the volume going across is constant. So this applies to all gases, and this has to do with the fact that the particle itself makes up a tremendously small portion of the overall volume of a gas because the gas particles themselves are very spread out. So it doesn't matter what gas particle you have. If you have equal volumes within that volume, you will have equal numbers of particles. By realizing this, Avogadro was able to also propose then Avogadro's, the mathematics that led to Avogadro's number, which we're all familiar with, 6.02 times 10 to the 23rd. So it doesn't matter the molar mass, whether I have something like helium or something like radon. If I am at a particular set of conditions, in this case STP, standard temperature, 273 Kelvin, and standard pressure, 1 atmosphere, the volume of 6.02 times 10 to the 23rd, or 1 mole of gas, will always be 22.4 liters. So 1 mole of gas, 22.4 liters, as long as you're at STP. Now, as we've learned in previous videos, if you're at different pressures and temperatures, of course that number will change, but at STP it's always 22.4. So because of Avogadro's law, if these three gases have the same number of particles, despite the fact they have very different masses and they're at the same temperature and pressure, they will occupy different volumes. Now their densities will be different. The helium is much lighter than air. Helium, the molar mass of a helium atom is around 4, whereas oxygen it's O2, so it'd be 32. Nitrogen is N2, so that'd be 28. Okay, this is a lot less dense than the surrounding air. So if you have a balloon filled with helium and release it, of course you all know that floats. The reverse is the opposite effect would be if you have a balloon filled with radon. Now, on top of being radioactive, radon has a very high molar mass. Its molar mass is 222 approximately. So again, that is way more dense than things like oxygen and nitrogen. So if you had a balloon filled with radon and let it go, it would drop. It would drop very, very quickly because it's very, very dense. But the point is the number of particles would be the same. The volume would be the same. Another illustration here, different gases, they occupy the same volume. They'll have the same or different numbers of molar masses based on their particles, and we talked about the oxygen and nitrogen in the last slide. But they still all contain 1 mole of gas, or 6.02 times 10 to the 23rd particles. Their pressure would all be 1 atmosphere, and their temperature is all 273. Now, another law that's important is called Dalton's law of partial pressures. Dalton's law simply says that the sum of the partial pressures of all the components in a gas mixture will equal the total pressure of the mixture. So if you were to actually write it out, it looks something like this. It's basically saying that the total pressure is equal to the pressure of each gas. It's called the partial pressure of each gas added together. So if you think about it, what's happening is if I have, let's say I have some oxygen particles and some nitrogen particles as an example. The oxygen particles are colliding with a container and they're exerting some pressure. The nitrogen particles are colliding with the container and exerting some pressure. Well, if I put both of those gases, simply the oxygen and nitrogen collisions with the container will sum up, and so then the total pressure would be equal to the sum of the pressures that both gases are exerting as they collide with their container. So as an example, if you have a flask containing a mixture of oxygen, argon, and carbon dioxide, and the pressure of just the oxygen is 745, the argon is 0.278 atmospheres, and the carbon dioxide is 321, what is the total pressure? So what's happening here is the oxygen particles are slamming into the sides of the container, exerting some pressure. This is how much they exert. The, what's my second gas? Argon is also colliding and exerting some pressure, and of course the CO2 as well. So if I want to know the total pressure, that's because I'm adding all of these gases together. Well, the oxygen's still there. It's still colliding and still exerting this amount of pressure. I've now added in the argon. They're still colliding and they're still exerting some pressure, and the carbon dioxide as well. So just put them all together and you'll get the total pressure. Now, the one trick with this one is they're not all in the same units. So of course we would have to convert that atmosphere to torr, just like the other two. And again, don't forget, you write down what's given, Those units go on the bottom, ATM. I'm going to torr. How many torr or millimeters of mercury are in what atmosphere? It's 760 to 1. So I'd fill in those numbers, do my math, and it's 211. So now to get my total pressure, I add that 211 to the 745 and the 391, and my total pressure would be 1,347 torr or millimeters of mercury. Again, just make sure your units are all in the same form. Another way of looking at this, to give you just a visual on this, if this is one gas, notice how it's striking the container, exerting some pressure. Here's another gas, B, it's striking, exerting some pressure. If I put both of them in the same container, again, the A or blue arrows are still in there doing their pressure. The red arrows, B, are doing their pressure. So again, to get the total pressure, I would simply add them all together. Again, another way of looking at this, if I have 8.4 atmospheres of pressure, 1.7 moles of helium. If I have 8.4 atmospheres of pressure, maybe it's 3 gases, but they're all going to add up to the same number of particles. If I have 8.4 over here, different gases, same thing. So as long as you have equal numbers of moles, the pressure all adds up to the same volume and the same pressure. So a problem that might go with something like this. The total pressure of a mixture is 498. If helium is 20% of the mixture, what's the partial pressure of helium in millimeters of mercury? So what they're telling me is the total pressure of the helium and neon is 498, and they're telling me 20% of that is my helium. So what I'm doing here is I turn my percentage into the decimal form. I made it 0.20. I'm multiplying that by the total pressure, so I'm finding 20% of this number. That's 99.6 millimeters of mercury for the helium. And again, that's all I really need to know for that problem.